Hello everyone, this is a tutorial on the Edge Turning Octahedron, which I will call ETO, and the Rua Puzzle. The Rua Puzzle is a shape modification of the ETO, where edges go to faces, vertices go to vertices. Now the difference is that the centers on the ETO have one color, while on the Rua Puzzle they have three colors. The edges have two colors on the ETO, and they just become triangular with one color on the faces of the Rua Puzzle, and these outer centers present on the ETO are not present anymore on the Rua Puzzle. These two puzzles are both jumbling puzzles. An important feature of the ETO is that the outer centers they stay in orbits. If I perform a 180-degree move on the ETO, I will swap the position of two outer centers, but they will stay on the same orbits. Orbits run between any two couple of faces. Since we have 8 faces, we have 4 orbits. The only way to swap the position of two outer centers between orbits is to use the jumbling move. Since the Rua Puzzle has no outer centers, they just disappear in the shape modification. This means that we can solve this puzzle without using the jumbling move. Each orbit has 6 colors out of the 8 colors of the puzzle, and the 2 colors missing are the color of the 2 faces the orbit is in between. I give name to the orbits based on the 2 faces or the 2 colors missing in the orbit. The Rua Puzzle is a mechanical subset of the ETO, and therefore it can be solved using the same method, just skipping all the steps involving the outer centers which are not present on the Rua Puzzle. I have made another video present in my channel specific to the Rua Puzzle, so if you got a Rua Puzzle, you may follow that video. The only thing is that when you come to the last step where you fix these triangles, you may want to use the method explained in this video, which is much improved with respect to the one I did in the last video. Notation. Since we can perform only 180 degrees move, it's not necessary to specify if the move is clockwise or anti-clockwise. I will call this edge up, this one front. Since we have 4 right, 4 left edges, then I'll use indices to further specify which edge I'm talking about. So for example, this will be the right up front edge, and this will be the left down back, and so on. When you fully scramble the ETO, it may lose its original shape and not be an octahedron anymore. So the first part of the solve is to work on the puzzle to give it its original shape. This is quite an intuitive step. There are no specific algorithms to do it, so I won't address it in this video. I'm sure you can do it playing a little bit with the puzzle. Just be careful, because when the puzzle has not its original shape, it tends to jump. So if you force too much, you may pop it. Once the puzzle is back to its original shape, we want to fix the orbits, meaning that we want to place pieces with the correct color in each orbit. This task is all about swapping pieces in the orbits using the jumbling move. For any 2 orbits, there are 2 faces next to each other, where also the orbits are facing each other. So if we want to swap, let's say, this piece from this orbit and this white one from this orbit, we need to bring the elements to swap to the 2 faces that are next to each other, and then we can apply the jumbling move. So the white that before was in this orbit is now in the other one, and the green that was in this orbit is on the other side. You can use any strategy you want to complete the orbits, as long as you can make it. I personally find very difficult to tell which orbit is which. So what I do, I place two blue pieces in one orbit, and I call this orbit the green and the orange. Two red pieces in another orbit, which for me is the gray and purple, and then two green pieces for the blue and red, and two orange pieces for the white and yellow orbit. So I can tell which orbit is which. At that point, I start fixing the orbits one by one, picking colors from an orbit I haven't fixed yet, till I get to the last one. And finally, I swap one blue and one red from two orbits, one green and one orange for the other two orbits, and so I get the orbit finally done. So, for example, I want this orbit to be the white and yellow, for example. I know that in the white and yellow I need to put two orange color pieces. One is already here, and the other one is, I follow the orbit, is here. So I put another orange in here. Okay, so now this is the orbit with two orange, one is this and one is this. This is the orbit with two red. There are three actually, but doesn't matter. This is the orbit with two blue, and this is the orbit with two green. So now I can tell which orbit is which. Once you have labeled all the orbits, putting two triangles of the same color in them, you can start fixing them one by one, swapping colors with the jumbling move, and picking colors from the orbit to an orbit that has not been fixed yet. For example, in this case, I've already fixed the green orbit, which is the one between the blue and red face. I have fix the orange, which is the one between the white and yellow. The next one I want to fix is the blue orbit, which is this one between I need to swap if any pieces from the red, which is the one I haven't fixed yet. So the blue should have white, yellow, gray and purple. Go purple, gray, but I got two white, so I need to pick one yellow from the red, which is this one. This is the yellow I want to pick. This is the white I want to swap. I put the two pieces to swap facing each other, and I perform the jumbling move. So now the green, the blue orbit, which is this one, has in it purple, white, yellow and green, and the red, which is the last one, of course will be fixed because it's the last one left, and it is the one with the white, yellow, green and orange. So we have yellow, orange, green and white. So all the orbits now have been fixed. Now that all the outer center have been placed in their own orbit, we still have two pieces of the same color in each orbit. So to really complete the orbit, we need to swap one red piece from the red orbit with the one piece from the blue orbit, and the same for the green and the orange. So we start from the red and blue. This is the red orbit. This is the blue orbit. We need to place the two pieces to swap facing each other, and we just perform the jumbling move. And we do the same for the orange orbit, which is this one, and the green orbit, which is this one. We place the green from the green orbit and the orange from the orange orbit facing each other, and we swap them using the jumbling move. Now the orbits are really fixed. Each orbit has 6 colors. There are no 2 colors in each orbit, and all the colors are where they are supposed to be. The next step is to fix the vertices. This is easy. We do it quite in an intuitive way. If you need to turn one vertices, you just make it go around a face where there are no vertices fixed till it matches with the color of the other one. This is white and green, which is here. We put it in place. Once again, we go around again till it matches with the other one. And this is, we are lucky, this is okay. The last two, we can just match them, but we need to orientate them, to turn them. When 4 vertices are in place and well oriented, we need to orient the last 2. And to do that, we use a 3 cycle that takes this vertex to this to this, and this to this, which is simple: right, left, right, left, and the opposite cycle that takes this to this to this, and this to this, which is left, right, left, right. As you see, permuting back the vertices doesn't change the orientation. To change the orientation, we need a setup move. The setup move is this one. We take this vertex here, and we take this vertex here. We perform the 3 cycle: right, left, right, left. We undo the setup move, and we perform the opposite side, which is left, right, left, right. You see, all the vertices now are in place and well oriented. Now that all the vertices are in place, which define the color of the faces, we need to be sure that each orbit is in the right position between the 2 faces. For example, this orbit is the red-blue orbit, because it has no red and no blue in it. It has all the other colors, no red, no blue. But it's between the purple and the orange and gray face. So to place this orbit between the 2 correct faces, we need to swap 2 faces. In particular, we want this red face to be here, just above its own orbit. And this can be done by the following algorithm: right, up, back, up, left, up, front, up, right, a back, up, and down. Now the red face is here, the blue face is here, and the orbit is in the red and blue orbit is in the correct position. And so we check for the other one. For example, this is the purple green. There is no purple, no green, so this is correct. This is the white, yellow, and also this is in the right position. Now each orbit is between the two faces where it is supposed to be. Before we proceed, we need to check that there is no center parity. The center parity happens because we will see later when we fix the center, we use a 3 cycle. And a 3 cycle on 8 elements, which are the 8 centers on the puzzle, they form a group. This group is a subgroup of the symmetric group you get by swapping elements. Now, this means that there are some configuration cannot be reached with a 3 cycle. If we have a parity and we try to fix the center with a 3 cycle, we will end up with the 2 elements to swap at the end, and we won't be able to to fix the centers. To check the parity, we need to check the cycles we have on the cube. For example, in this case, we start from the white. We have the white goes to blue, one, gray, 2, purple, 3, yellow, 4, and white. We are back to white. 5. This is a 5 cycle. Then we have red is in red, and we have a 2 cycle. Orange and green, 1 and 2. This is a 2 cycle. So we have a 2 cycle and a 5 cycle. This is a parity. The rule is that if we have an odd number or even cycle, then we have a parity. For example, 3 2 cycle is a parity. A 6 cycle is a parity, but for example, a 6 cycle and a 2 cycle is not a parity. The center parity happens because at the very beginning, when we name the orbits, we swap 2 orbits. So the only way to solve it is to swap any 2 orbits back. For example, I swap the blue and red orbit with the white and yellow. And to do that, I swap the white from the blue and red with the blue from the white and yellow orbit, and the yellow from the blue and red with the red from the white and yellow orbit. So let's start. We swap the white of the blue and red orbit, which is this one, with the blue of the white and yellow. So we place the 2 pieces to swap one in front of another, so they face them, and we apply the jumbling move. And the second piece to swap is the yellow from the red and blue orbit, which is this one, with the red from the white and yellow. So we face the 2, and again we apply the jumbling move. Okay, now that the two orbits are swapped, unfortunately we have messed up the puzzle. So we have to go back to the beginning to fix again the vertices and then to place the orbits between the two correct faces. But at the end, we will see that the parity is not present anymore. Okay, I've fixed the vertices again. I've put the correct orbit between the two correct faces, and then we can check if the parity is solved. We start from the blue. We have red 1, 2, 3, 4, 5, 6, and 7. We have a 7 cycle, which is odd, and we must have one in place. The white is in the correct. So we have a 7 cycle. The center parity is solved. The next step is to fix the pieces, the outer center, in each orbit with an algorithm with a 3 cycle between 3 elements next to each other. If we place the puzzle in this way with the third element in the 3 cycle hidden on the back, there are 2 versions of the algorithm. One that will put the orange to the green to the purple, and the purple back here. I call it the up algorithm because from what I see here they go up, and then there is the down version of the algorithm which take the green to the orange to the purple to the green. We start from the up version, which is front, left up front, right up front, left up front, front, left up front, right up front, left up front. The 3 cycle preserves the position of the vertices, and then there is the down version, which now I will apply. I will put these 3 back to the original position, which is almost the same, but I swap the front move with the move on the right and left. So I do the left up front, right up front, left front first, then the front, and then I do again left, right, left, and we are back to the previous position. Sometimes you need to orient the puzzle in the correct way. Sometimes you can just do, for example, the yellow has to go here. I can find the position, so if I want the yellow here, I will place it like this with the yellow, the piece I'm working on, maybe hidden, and I will apply a down algorithm. There is always a way to orient the puzzle and to do what I want. The final aim is to put each place in the correct position. The final aim of this step is to put every outer center on the correct face. Face color is given by, of course, by the vertices. Sometimes you cannot complete this task because to move pieces on the orbit we have a 3 cycle, but you may end up in a situation like this where you have 2 pieces left to swap, and we know that with a 3 cycle we cannot swap 2 pieces. All the other pieces are in place. In this case, we say that this orbit has a parity. A parity cannot be solved. We need to find another orbit with a parity. For example, here we have blue, the blue should be, the white should be here, and the blue should be here. All the other pieces are in place. Once we have two orbits with a parity, one is this, and the other orbit is this. These are the two orbits. We need to find two faces that give name to the orbits. And we put these two faces in this position, and we apply this algorithm. Right, left, right, left, right, left. This algorithm will fix the parity for the two orbits. Then we can go back and using the algorithm as before, we can fix it. You may end up in a situation where only one orbit has a parity, like in this case, these two pieces are swapped, and they are the only one. There is no other orbit with a parity, so I cannot use the algorithm I showed you before to fix this parity. This happens when two pieces of the same color from any two orbits are swapped. So to solve this parity, we need to swap any two pieces of the same color between two orbits. For example, we may swap this red and this red, which belong to two different orbits. We take this red here, and we take this red here. As usual, they need to face each other, and we can apply the jumbling move to swap them. Here we go. Unfortunately, this will mess up the puzzle. Hopefully not too much. So you have to go back and to start from the beginning. You don't need to fix the orbit anymore, but you need to start from the vertices and so on. Once all the outer centers are fixed, it's time now to fix the centers. We do it again with a 3 cycle. We have the clockwise version, which is this goes down, the red will go to the red and the white here, which is up, left up front, up, right up front, up, left up front, up, left up front, and this is fixed. And then we have the symmetric, which goes anti-clockwise. Let's see where we can apply it. We go anti-clockwise, which is up, right up front, up, left up front, up, right up front, up, left up front. Okay, let's see, we want to put the yellow, the white here. Again, we go anti-clockwise, so it's up, right up front, up, left up front, up, right up front, up, left up front. These one are fixed. This is in place since we checked the parity at the beginning. We are sure that we can make it. We go clockwise this time, up, left up front, up, right up front, up, left up front, up, right up front, and all the centers are fixed. For the Rua puzzle, fixing the center is a bit different because on this puzzle, centers have 3 colors, which is different from the ETO, and therefore you need to place centers in the correct position and orient them. To do that, you need a specific algorithm, and for those algorithms, you can have a look to the other video I did on my channel, specific to the Rua puzzle. However, for the triangles, as I said before, you really want to stick to this video, where the method for fixing the triangle is much improved with the one present in the other video. In the last step, we need to fix the edges, which are these little triangles. And once again, the way we do it is by means of 3 cycles. There are basically 2 3 cycles we use. The first one, which I call algorithm A1, is the one cycling these 3 pieces, these 2 on the top and this one in the bottom, in this way. For example, in this case, if I cycle these 3 pieces, I will put this edge here, which is its correct position. The algorithm goes like that: back, left up back, left down front, left up back, back, up, and we repeat again: back, left up back, left down front, left up back, back and front. And you see we have this piece in place. The second algorithm, which I call A2, is an algorithm that cycles this piece here on the back edge, down back, with these 2 in this way. So for example, in this case, we want to put the gray and blue here. So we perform this algorithm. Is left up front, right up front, left up front, right up front, up, front, up, and then right up front, left up front, right up front, left up front, up, front, up. And you see the edge is gone in place. We have also another algorithm, which is really not a new one, but just the algorithm A2, the symmetric of it, which cycle the edge on the other side with these 2. And it's just the symmetric of the previous one. It goes like that: right up front, left up front, right up front, left up front, up, front, up, and left up front, right up front, left up front, right up front, up, front, up, and the edge that was here now is here. Using the 2 plus 1, 3 cycles I've shown you. You can basically cycle between any 3 edges you want by just adding setups moves. This is a table in which I showed the basic setups move you need to cycle between edges, mainly in the front part of the puzzle. For example, I will show how algorithm A7 works. We want to cycle this piece here, this here, and this here. So this will go in place. Since we can cycle from this side, we need to take this piece to the other side of the cube. We do that by putting the piece up on the back and then in position here. Now, because by cycling this way we will move the piece here, but we want the piece here, we need to undo the first move of the 3 cycle. And then we proceed. We have left, right, left, right, up, front, up, right, left, right, left, up, sorry, up, front, up. This was algorithm A2, which is a cycle from these 3 pieces. Now we need to undo the setup move. So first of all, we undo this move here, and then we take this piece up here on this side, sorry, on this side, and finally down. And you see the piece has gone in the correct position. Thanks for watching.